Hi guys, it's Robbie Wyness here today. Today I want to talk to you guys about specific heat capacity problems, and at the end of the video I'll show you guys where you can download this workbook we have for specific heat. It covers what is specific heat, the equation, the formula variables for the equation. It also goes over the two questions that we're going to cover. The first question, I believe the majority of you guys will get it right. It's pretty straightforward. But the second question we have here, this question, I see a lot of people in our online course, they'll end up getting a negative variable for the specific heat. In the training today, I'll cover how the two most common mistakes that I see them make, and it's also highlighted in here for you guys. So I recommend that you print this off and go work through these problems a couple times. I know when I was studying for my exams, it helped a lot more once I'd write them out a couple times. I definitely understood how to do it a lot better. So I'll tell you how you can download that at the end of the video, and I guess let's get into the tutorial today. So what is specific heat capacity? Specific heat capacity of a substance is defined as the amount of heat energy required to raise the temperature of a unit mass of that substance by 1 degree Kelvin or 1 degree Celsius. So given that definition above, we can conclude that the quantity of heat energy transferred to a substance is dependent upon the following variables. It's the overall mass of the substance, the specific heat to that particular substance, and the temperature increase or decrease experienced by the substance. The specific heat capacity formula, it's commonly written as Q equals MC delta T. You might see it as Q equals MC T2 minus T1. The formula variables, Q is the quantity of heat added or removed, M is the mass of the substance, C is the specific heat of the substance, delta T, that's change in temperature. It's T2 minus T1. T2 is the final temperature and T1 is your initial temperature. An important note, sometimes you'll see the temperature variables are provided in degrees Celsius or degrees Kelvin. As long as they're both in degrees Celsius or degrees Kelvin, it'll make no difference of your final temperature change. So I guess to explain that one way, I guess we could do if we had 5 degrees Celsius for our initial and 10 degrees Celsius was our final. Let's say this is T1, this is T2, so T2 minus T1 equals 10 minus 5. That would be 5 degrees Celsius is our delta. If this was converted to Kelvin, your T1 would be 5 plus 273, that's 278 Kelvin. Your T2, that'd be 10 plus 273, that's 283 Kelvin. So same thing, that would be 283 minus 278. That gives you the same delta as 5 degrees. And remember, Kelvin, that's your absolute temperature formula, so Kelvin equals degrees C plus 273. So the first question we have here is determine the quantity of heat to be transferred to 3.25 kilograms of cobalt to raise the temperature from 40 degrees to 220 degrees. Take the specific heat of cobalt is 0.402 kilojoules per kilogram Kelvin. So out of our 5 steps, the first step is always to write out your equation that you're going to use to solve the problem. So Q, which is the heat added or removed, that's in kilojoules. You got your mass, which is in kilograms, times your specific heat, which is in kilojoules per kilogram Celsius, times your temperature change, which is T2 minus T1 in degrees C. Step 2, you got to define all your variables and show their units. So Q, that's in this case, we're adding heat to raise the temperature from 40 degrees to 220 degrees. So that's the heat added and that's in kilojoules. That's our unknown. We have our mass, which is m, so that's the mass of cobalt. And that's in kilograms. That's 3.25 kilograms. C, that's the specific heat of cobalt. And that's in kilojoules per kilogram Celsius. And they provided us with that. That's 0.402 kilojoules per kilogram Celsius, or T1. That's our initial temperature. That's in degrees Celsius. That's 40 degrees C. T2, that's our final temperature. That's also in degrees Celsius. That's 220 degrees. So our third step out of the 5 steps is state your assumptions. So the one assumption we'll have is that while the heat's being transferred to 3.25 kilograms of cobalt to increase the temperature, none of the heat is lost to the surroundings. So the fourth step, that's your solution. Make sure you guys show all your steps and check the units in each step. So we write our equation again. Q, the heat added in kilojoules, your mass, kilograms, times your specific heat is kilojoules per kilogram 0C, and times your temperature rise, which is T2 minus T1 in degrees C. So we put in our variables. That's 3.25 kilograms times 0.402 kilojoules per kilogram 0C times your T2, which is your final temperature. That was 220 degrees C, minus 40 degrees C, your T1, your initial temperature. So if you minus 40 from 220, you'll get 180 degrees C as your delta temperature change. So if we cancel out the units between the numerator and denominator, you can cancel out your Celsius, you can cancel out your kilograms. And if you times all these together, you'll get, so I guess 3.25 times 0.402 times 180, that's 235.17 kilojoules. So the last step, I always like to write out your final answer. So step 5, state your final answer. The quantity of heat that needs to be transferred to increase the temperature of cobalt from 40 degrees to 220 degrees is 235.17 kilojoules. So our last question here, the one that I see quite a few people struggle with, is calculate the specific heat and what the 1,000 kilogram substance is when 125.49 megajoules is required to be removed from the substance to decrease the temperature from 50 degrees C to 20 degrees C. So first things first, I'll just write out the equation we're going to use. So I'm going to use the specific heat equation again. That's Q, kilojoules, got your M, your mass, times your specific heat, kilojoules per kilogram 0C, times your temperature change, which is T2 minus T1 in degrees C. So to find all variables, Once again, you got Q. In this case, the heat's removed, so this is the heat removed, and that's in kilojoule. So they provided us with it in megajoules, so that is 125. I guess it's negative. See, that's one areas where people go wrong, is if it's being removed from the substance. I like to put it's negative 125.49 because it's being removed, not added. So to convert that to kilojoules, we would times that by, there's 1,000 kilojoules per megajoule. So megajoules can cross out, you're left with kilojoules, so that's 125,000, I guess negative 125,490 kilojoules is the quantity of heat removed. Our specific heat, that's our unknown. That's what we're trying to solve for. And that's in kilojoules per kilogram Celsius. It's our unknown. We have our mass. We don't know what the substance is. That's in kilograms. It's 1,000 kilograms. And our T1, which is our initial temperature, it's in degrees Celsius. Our initial temperature was 50 degrees C. Our T2, that's our final temperature. And that's 20 degrees. So, step number 3, state your assumptions. We'll assume that when the heat's being removed, none of it's lost to the surroundings, Step number 4 is your solution. Show all steps and check your units in each step. So once again, get your Q. Whoops. That's in kilojoules. Equals M, your mass, in kilograms times your specific heat. Just kilojoules per kilogram Celsius. Times your temperature rise, T2 minus T1 degrees C. So we put all our variables in. That's 125,000, I guess negative, 490 kilojoules equals 1,000 kilograms times your specific heat, which we don't know, times your temperature rise. So your T2, your final temperature is 20 degrees C minus your initial temperature, which is 50 degrees C. So if we solve in the brackets, 20 minus 50, that gives you negative 30 degrees C. So 1,000 kilograms times C times negative 30 degrees C. So if we rearrange the formula now to get specific heat by itself, you would have to go 1,000 kilograms minus 30. Do that to each side. So on this side, same thing. 1,000 kilograms times negative 30 C. So over here, got your numerator, denominator. These cross out. So you're left with C, your specific heat, equals negative 125,490 kilojoules over 100 kilograms times negative 30 degrees C. You times 1,000 kilograms by 30. That'll give you 30,000. So that'd be negative. I guess it'll be negative 30,000 because you got your negative. So negative 125, 490 kilojoules over negative 30,000 kilograms degrees C. So when you divide 125,490 by 30,000, you'll get 4.183 kilojoules per kilogram 0C. That's your specific heat. The one reason I like writing out like our variables, I guess, yeah, our variables in their units is you can see our specific heat. We want our final answer to be in kilojoules per kilogram Celsius. So when we carried our units through, and then like when cross them out, at the end we were left with kilojoules per kilogram Celsius. So it helps kind of if you miss a step, like the units, they won't make sense. They won't be, I guess, what you want your final answer to be. It'll kind of help you catch a mistake before you come up with your final answer. So it's a good practice, even though it takes a little longer, but just always write your units out. So step 5, that's our state your final answer. The specific heat of the unknown substance, that's 4.183 kilojoules per kilogram Celsius. And the unknown substance, it'd be most likely water. Water has the same specific heat as 4.183. So the mistakes I'm seeing a lot of people making on this question is for the heat removed. You can see even I was forgetting the negative sign in front of it a couple times. If I forgot the negative sign here, this would be positive. If I did this correctly, my T2 and T1, I'd have negative 30. I'd end up with negative 4.183. And the other one that I commonly see is they do have the negative there because the heat's removed, but they'll just lose it. Like somewhere in the equation like this, they might put 50 minus 20, and then they'll have negative 125,490 and positive 30,000 kilograms per Celsius, and they'll get a negative specific heat. Not that it makes a huge difference. I mean, you had all the steps correct, so you'd still get the majority of your marks, but that is a mistake that I'm seeing people make. And I guess the one last thing is in the description below, we'll have a link where you can download this workbook, and I highly recommend it. Download it, print it off, get a couple of blank pieces of paper, and just work through the questions until you can get the correct answer without having to look back at, the workbook itself. If you guys like these type of videos, hit the like button down below, and if you're working on your 2A2, preparing for that exam, I'd recommend subscribing to the channel. We're uploading at least one new video every week on a topic that's on the syllabus to prepare for the exam. So we'll talk to you guys in the next video.